Hi, I'm Elaine and I'm going to give you an example of Huffman coding which you can use for revision. So as you hopefully know, most ASCII files consist of 8-bit characters to represent each letter. So a capital S is represented by decimal 83, which is shown in binary format just below, and lowercase s is in decimal 115, which is shown below. So there are 8 bits used to represent each letter. Here's an example of the ASCII table. So you can go to asciitable.com to see each of the values for the different letters, whether they're uppercase or lowercase. So remember, they are different and they're to be treated differently. Now, compression is all about reducing the file size. So if every character is represented as 8 bits, what you need to do is try to make that shorter. So the idea of Huffman coding is to generate codes, unique codes for each letter that are represented in a file, which are a lot smaller than the ASCII representation, in the hope that you will reduce the file size. So I'm going to show you a couple of examples now on how to do this. I'm going to give you an example using a very short phrase. And what you need to do is follow this sequence. This is the algorithm for Huffman coding. So I'm going to write all in uppercase just to make things nice and straightforward. She space sells seashells. Now you can work along with this or do this and then have another go yourself. So what the algorithm is to find the frequency of occurrence of each letter in the file. So in this file, let's write down all of the letters that we have. We have an S, a H, an E, a space, L, A. So I think that covers it. So we have an S, a H, an E, a space, an L, and an A. That covers it. So I'll cross each one out just to make sure that you can see I've counted it. So we have 1, 2, 3, 4, 5. We have 6 S's. In terms of H's, we have 1, 2 H's. For an E, we have 1, 2, 3, 4 E's. With 1, 2, 3 spaces. We have 4 L's and 1 A, and hopefully that's all catered for. Yeah, all of those catered for. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 characters, which would be 160 bits if represented in ASCII. So now what I need to do is show you the next step. The computer builds a queue in memory, and that queue will be in order of frequency. So I will draw that now. Sorry about this messiness. And I will give quite a reasonable amount of space just so that I can add to this queue as we go along. So H, so in order of frequency, A being 1, H being 2, space being 3, E being 4, L being 4 as well. So I'm making a queue. So imagine the computer program now is building a queue in memory. That's what would be happening. Just make sure I have everything represented here. 1, 2, 3, 4, 5, 6 things. 1, 2, 3, 4, 5, 6 characters. Now what the computer needs to do is start building a binary tree. And I will show you this as a part of this demonstration. So take the first 2 minimal frequency values to make the first node. A1, H2. And what I'm going to do is change the colour when I have an internal node, so you can see that's 3, and I'm going to place an internal node in the next place in order, because everything is in order of lowest frequency. So that's going to be a 3. These two are popped off the, or taken off the queue, so we'll take those away with the red or the eraser. I'll erase those, they've gone now. Okay, so they're no longer in the queue. And the next thing that I need to do is join the next two minimal values, which are these two here. So add my space. Let's get some consistency here. A space is 3, and join that to here, and use blue again to create my next internal value, which is 6, and that needs to go up here. So I'll create my new internal. I know you can't read that very well, but if I put that there, and then what I'm going to do is take the eraser and scrub out the two that I've just joined together. And now that's what's in the queue. So now what I need to do is take my next two minimal or low frequency values and join them up together. So I'm taking my E4 and L4, join those together to make a new internal node of 8, which is placed in order in the queue. So that goes here, internal node that is, and remove the items that I have just joined from the queue. So they've now gone. You might want to just cross them out or something like that if you're doing this on paper. So now what we need to do is join those two together. So join 6 with 6. So we need to put S here. I need the pen S6 to be joined with this one. Let me do that again because it's a bit messy. I started to join it straight to it then. Okay, so join those together, and again the creation of a new internal node gives you 12. So I'll add that to the bottom. Not that I need to now, but just to show you how this works. And then delete the two that we have just dealt with, so they get taken out of memory once they are dealt with. And finally the last two, which are the remaining nodes, are joined together using the same formula, so repetitive formula, which creates a final new internal node. They then disappear, and we have our final value, which is equal to the number of bits that we started with. Let me fix that. I just looked at a different number. So that is your 20. So we have 20, 6, 7, 8, 12, 15, 19, 20. 20 different characters represented here by 120 bits. Now what we need to do is we need to make this into the binary tree. So each branch is given a value. The left is given the lower number and the right branches are given the higher number. So left 0, right 1, left 0, right 1, left 0, right 1, left 0, right 1. This enables us now to give each letter a code. So this node here represents allows you to get to an E and an L. This one allows you to get to S space H A. This node here allows you to get to space H and A. And so as you can see, this one lets you go to a H and an A, but this is all represented internally in the computer's memory, and this tree is what is transmitted with your code. Now you would imagine that that would be quite an overhead along with just a small file, therefore you wouldn't want to compress such a small file, so we're looking at large files here, otherwise there is no point, especially when you have to send the binary tree for encoding. So to create the code from the tree which is transmitted, you would start off with your S. So S is represented as 1 0, that's a 1 0, and then you have a H which is represented as 1 1 1 0, 1 1 1 0, and an E which is a 0 0, and then you have your space which is 1 1 0, and again back to your S, 1 0, and E, 0 0, L, and you can go on like this, so 0 1. I'll just write down the codes for each of these letters next to them so that you can actually see what those codes are. 1 2 3 4, E is 0 0, space 1 1 0, L is 0 1, and then A is 1 1 1 1. You will notice none of these are a prefix of any of the other codes, so you cannot mistake when the computer starts to encode this. It gets to the 1 and finds 4 possibilities, and then it reads the next one and there is only one possibility. It finds the S and ends there. It's found its letter. Then starts again and think, oh right, okay, there are 4 at this point possibilities, and then there are 3 at this point possibilities, but still hasn't found it yet. And then it gets the next one and there are 2 possibilities, and then it gets to the next one and there is only 1 possibility, which is the H, and then it ends its reading there. Starts again and finds a 0, and there are 2 possibilities, finds a 0 next to it, there's only 1 possibility. So hopefully you can see nothing is a prefix of the next, no spaces or gaps are needed. This can be just stored like this. Like this, without any gaps, as long as the binary tree is transmitted with the data, the compressed data, and it'll be in this format. You should be also able now to deduce the fact that for 2 bits, if you have 6 S's, you are only going to need 12 bits. So I'll just write this in green. So 12 bits are needed for your S's. 1 2 3 4 bits times 2, so 8 bits are needed for your H's. 4 times 2, 8 bits are needed for your E's. 9, so 3 times 3, 9 bits. 4 L's, 2 bits, so that's 8 bits. And 1 A, so that's 4 bits. You will find that the highest frequency items had just 2 bits to represent them, and the lowest frequency had 4 bits, and those in the middle had 3. So you could see that the highest frequency did actually in fact end up with the lowest number of bits to represent them, which is what you want, because I've got 12 bits to represent my S's, of which there are 6. So that would have been 6 times 8, 48 bits, so down from 48 bits. And here that would have been 16 bits, so that's halved. And here your E would have been 4 lots, that would have been 32, so that's a quarter. And your space would have been 24, so that's a bit less than half. Okay, so that's instead of 24, down from 24 bits. L's would have been 32, so that's a quarter. These are nice easy ones, so I can put these as fractions. And that is half. So you can already see there's a good reduction there. Now add these up, and that's 28, 37, 45, 49 bits. So 49 bits instead of 160. So down from 160. So hopefully that gives you a good idea of how to do Huffman coding. Why don't you have a go now? I'm going to put learn and learn it well. I'm going to take my time, and hopefully you can go along with this. So remember the spaces. I don't want to use the same one because I don't want you to get just one example. What do we do first? We write down the frequencies of each letter. So 1 L, 2, 4 L's. E, 3, A, 3, R, how many of those? 2. You try to do this. Pause it if you have to. Space. Do not forget the space. They are characters. Good test. Add them all up. Make sure they match the number of characters that you have. $23. I didn't mean to have an S on the end there. Let me just check that. I don't know why that S is there, or did I really put that S there? Learn and learn it well. Okay, so that's good. That's now 23 characters. 23 characters represented as ASCII times 8 bits is what? What do you think it is? Well, you'll use a calculator, I reckon. Well, maybe some of you know maths quite well. So put these in order, and that could be a case of the computer building a queue. Let's do that. So we can put all of our single frequency letters at the top. D, I, T, W, followed by the next one, which is, yep, R. And then we have a couple of 3s there, so put those in. And a couple of 4s. And that is the queue that's been built. I will use another colour pen to indicate where an internal node has been placed, just to make it easier. So this is the queue built by the computer, and again it's always useful to put the frequency there just to make it a little easier to refer to and do the addition. The computer can do this a lot quicker, a lot easier than the human. So that's my reference data. So the next rule is, can you remember? Build the binary tree. Alright, build the tree. So take the minimal nodes and make a node out of them. So D1 and I1 build the tree and end up with 2, and that gives you your new node, which I will put in a different colour here. I hope that's sufficient to distinguish between it. So that's our new internal node, and that is a value of 2. And what I'll do is I'll just cross out these two so I can keep them in place for this example so that you can refer back to it. And then we go back and we select our next 2, which is going to be here, and build our next tree, internal node, and that is 2 as well. So we now have another one with 2. Let me alter this slightly. So that's an R there, and that's an R2, and then remove the items from the queue that we have now dealt with. So we now have 2 and 2 internal nodes. So 1, 2, 3, 4, and then 2 internal nodes have been created, which allow us access. This one allows us access to TW, and this one to DI. Next is the next 2 minimal nodes are to be joined. So I'm going to remove these 2 off the queue, dealt with, and join them together using the same strategy that has been used, and create a new internal node. And hopefully you're following this okay, and that can be created here, internal, with a value of 4, a frequency value of 4. So I've removed those now, and the next 2 minimal values for me to start removing are the R and the E. So I now need to make a new node with an R and an E. Now I might need to move these around shortly, could become a little bit of a mess, but I'm not too worried just yet. So that's 5, which gives us access to our R and E, and we put the new internal node at the bottom here, which is the 5, and remove the R and the E, which I have done, and I'm now going to build 2 more, which are A and N. Like I said, this one is going to get particularly messy, so I will be moving these shortly, I'm sure of it, and that gives us a 6, which I'm going to put down here. So I have 2 new internal nodes, and the A and the N have now disappeared, and the next 2 minimal nodes are the internal 4 and the space. So what I need to do is put the space 4 there and join these to create myself a new internal node, which I'm just going to put an arrow and say there's another one down there, and there we have quite a lot represented, and then we have these 2 on their own. So I have now gotten rid of these space, and now I have the L and the 5, the L and the 5. So let's put the L with the 5, and the L is a 4, so that gives us a 9. Alright, and that gives us yet another internal node. Now I would have to write a bit more on this, so I have got rid of my L and my 5. Let me just put that in red, that needs to go, and now I have my 6 and my 8 to join together. So my 8 and my 6 are my next two, because I've gotten rid of that one. So my 8 and my 6, so this one here is going to have to move. I'm going to move that out and reposition it somewhere else, using my mouse to put it where I want it. I'll move that out, move that again in a moment. I'll just put that out of the way and select this lot and move it in, because I'm now about to join those together. That was nice and easy. We've used paint to do this. So that's 14, because that's joining these two internal nodes together. So I'm going to cross the 8 and now I just have the 9. So the 14 is another internal node that I would have added to the end of the queue. So 9 and 14 need to go together. Let me reposition the 9 just to make it a bit easier, and that's now going to be added. Oops, sorry, back to my paint, to make my final internal node of 23. Notice that matches here, it matches here, and therefore it's correct. So I've built the tree, and now I've got to go ahead, and what I want to see here is that these guys here, L, E and A, have the highest, the smallest code, and these have the longest code. I mean, you don't want any of them to have a long code, but the longest of the options available. So go to the left of each node and label them up with a 0. The left of each node gets a 0, and the right of each node gets a 1. 0 and 1, because it's a binary tree, you only have 0 or 1 as options. And then we can use this to encode or create the codes for each of our letters. So let's look at what we have now. We have an L is a 0, 0, an E is 0, 1, 1, an A is 1, 0, 0, 1, 0, 0, and R is 0, 1, 0. Can you see that they have the lower frequency, the fewest number of bits? A space is 1, 1, 0, and nothing is a prefix of anything else so far, which is great. So we're now going to go to our single characters. D is 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. I is 1, 1, 1, 1, 1, all the ones. T is 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, and W is 1, 1, 1, so 3 ones, 0, 1. And there you have it. So to actually write, learn it well, it would be 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, with the N. I haven't put the N there. So let's do N. Sorry, I forgot to N. 1, 0, 1. So 1, 0, 1, and then we have the space 1, 1, 0, and then and 1, 0, 0, AN 1, 0, 1, D 1, 2, 3, 4, 5. As you can see, if this tree was transmitted on this file, the encoded file, this one, so this and the tree were sent, it would be able to work out, the computer, the algorithm would be able to work out that again it encounters the 0, and there are 1, 2, 3 possibilities. So the next character is a 0, which means there is only one possibility, giving you the L. Start again to the next letter. 0, again 1, 2, 3 possibilities with a 1, giving you 2 possibilities. And then the next one makes it clear that there's a possibility of an E there. So that's done. Start again. Starts off with the 1, encounters a 0 and a 0, which means it can stop. It's now found a letter with that code, and so it can start again. And there's a 0, it could be an E, it could be an R, or it could be an L. So let's go to the next letter. It could be an E or an R. Let's go to the next letter. It's just an R, but it's found one, and therefore it can stop and start again, and so on. And you will see that there are only 2 bits for the letter L, so that means you have, if I put in green how many bits will be used to represent that, 4 lots of 2, which is 8 bits, 3 lots of 3, which is 9 bits, because there are 3 bits for an E and we need 3 of them. A's, there are 3 bits and we need 3 of them, 9. 2 R's, 3 bits, 6. 3 N's, 3 bits, 9 bits. 4 spaces, spaces have got 3 bits, that's 12. D's, there's 1 D and 5 bits, and all of the others have got 5 bits. And in terms of the number of bits to represent, instead of your 184, you have 73 bits. So that's 73 bits instead of 2 S's. I like S's. So instead of that, which is pretty good, it's not quite a third, but it's reasonable. There's less frequency compared to she-cell seashells, but in some cases where there are more occurrences of certain letters, this would be a good algorithm. Anyway, hopefully that has given you an example and helped you to revise Huffman coding. And I'll stop there.